Okay, can everyone see this?
Yep.
Okay, great. So my topic is on dynamic programming, and soon you can find my website, johncanco.com. It's not up yet. It's really just a Mexican restaurant website right now. So this is hopefully one of a many-part technical series on algorithms and acing the technical interview. Okay, so the goals of this talk is to provide a very, very high-level explanation. So it's going to be a little bit rough, and so I'm favoring accessibility and intuition over academic precision. But this should pave the road for you to learn about all the different use cases and exceptions and nuances later on. Okay, so dynamic programming is used to answer the very simple question of, given a lot of ways to do something, what is the best way to do it? So here's a couple of examples. The first is the knapsack problem, which is we have a knapsack that can hold 8 pounds and items of various weights and values. What is the maximum value we can put into the knapsack? So the knapsack can hold 8 pounds, and you can only put a certain amount of items in here, and you have to choose which ones to increase the value in the knapsack. The second one is we have coins worth 1 cent, 2 cents, and 3 cents. How many ways are there to make 5 cents? And the third one is given 2 different strings, find the longest common subsequence. So for instance, ABCDAF and ACBCF, these are the letters, and so the longest common subsequence is 4. So what do these 3 questions have in common is that it's all about a lot of different ways to make 5 cents, to put things into a knapsack, and what's the best way. So you can think about dynamic programming as an algorithm that solves questions dealing with combinations or many different ways of doing something. So the knapsack problem. So again, you have these 4 different items of different weights and values, and how can you optimize what you're putting into the knapsack? So I've drawn it out in terms of just slots and squares. So we're trying to maximize what we put into these basically 8 slots. Okay, so step 1 for dynamic programming is to work backwards. You want to reason about the structure of the optimal solution. So imagine what the final result is. So we've tried to optimize everything that we're putting into the knapsack, and it could look a lot of different ways, right? So it could all be entirely filled. We put all the items in there that we can, and it perfectly fills up the 8 pounds in the knapsack. Or maybe, in these 2 cases, there were just some slots left over because the next most valuable item that we try to put in, it just doesn't fit. There's just not enough room in the knapsack. But either way, we can be sure about one thing, which is that an item is either in the final solution or it's not in the final solution. It's one or the other. It can't be both, right? So more specifically, if we were to just pick a specific item, so let's just say item 4. Item 4 is either in the final solution or it's not in the final solution. It's one or the other. I'm just using item 4 for this thought experiment. It doesn't matter which item you choose. So again, there are only 2 possibilities. Case 1, item 4 is in the optimal solution. So given this knapsack with a bunch of items in there, it's gray, so we don't know what's in there. But in this case, we say that item 4 is in the optimal solution. So it's taking up these 4 slots because this is what we're assuming for this case. Well, if that's true, then, okay, so there's also the second case, which is that item 4 is not in the optimal solution. So for instance, as an example, in here, item 4 just doesn't fit into this space. There's just not enough room. So again, so for case 1, if we assume that it fits into these 4 slots, what happens is now we have a new question. What is the maximum value we can put into a knapsack which only holds 4 pounds? So if we optimize this with this item 4, what's the maximum value that goes into this space? So basically, we've reduced the problem into a lot smaller of a problem, which is how can you optimize 4 slots? So case 2, again, is that item 4 is not in the optimal solution. So in the second scenario, there's just not enough room. You can't put it in there. Well, then the new insight we gain is that the optimal value of an 8-pound knapsack is actually the same as a 5-pound capacity knapsack, because there's these 3 slots that we can't use it because we just can't fit the items in there. So The new subproblem is, what is the maximum value we can put into a knapsack which can hold 5 pounds? And again, this would be with the remaining 3 items. How can we optimize this space? But what we figured out is that you can actually decompose this problem. And the solution to the final problem of how do you use 4 items in 8 spaces is actually composed of solutions to smaller, simpler problems. And so it's kind of like recursive dynamic programming. But for dynamic programming, we actually go bottom up. So we build up all these individual cases into the final solution because it's just more efficient that way. Okay, so step 3 is to go bottom up. So you solve the base states or the zeroth states and you build up to the final optimal solution. So for the zeroth state is if we have 0 items and we have a knapsack that can hold 0 pounds, what's the maximum value we can put into a 0 pound capacity knapsack? And that's 0. And so we filled out the zeros through here, and the rest will make sense right now. Okay, so you just keep going through the table. So if we just have item 1, which has a value of 15 and weighs 1 pound, what's the maximum that we can put into a 1 pound knapsack? Well, it's 15. And same thing throughout here because we only have 1 item and we just put it into the knapsack. So now we have items 0, 1, and 2. And what's the maximum that we can put into a 1 pound knapsack? Well, it's still 15 because item 2 weighs 5 pounds. So we can't put it into a 1 pound knapsack. But if we go to a 6 pound knapsack, what's the maximum we can put in here? If we have items 0, 1, and 2, well, we can put item 2 in here because it weighs 5 pounds. And so we have 1 pound remaining in this knapsack. And then what we do is what's the optimal value we can put into a 1 pound knapsack? Well, we already solved it earlier on. It's 15 right here. So you keep going through like that. And so for a 4 pound capacity knapsack, what's the maximum we can put in here when we have items 0, 1, 2, and 3? Well, we put item 3 in here to begin with. And so we have 1 pound left over, and we just go up to the previous column right here. And 15 right here is the maximum value we can put into a 1 pound knapsack with items 0, 1, and 2. So again, it was kind of like the earlier subproblem. So we continue going through the graph, and we get to an 8 pound knapsack with items 0, 1, 2, 3, and 4. So we put item 4 in here, and that leaves a remainder of 4. So what's the maximum value we can put into a 4 pound knapsack with items 0, 1, 2, and 3? Well, it's 24. So 24 plus 5 gives us 29. And so the final optimal value for items 0, 1, 2, 3, and 4 is this plus this subproblem, which we already solved earlier on. And that's the lightning talk.
That was awesome, dude.
Thanks.
Super good. Sorry about that. I was muted. Does anybody have any questions for John?
Have you used this in actual real-world problem solving?
No, so this is just for me to prep for technical interviews. I just started that process, so it's been going through a lot of these different algorithms.
Yeah,
Do you see a situation where it would come in handy over something else that we've learned? A more rational way of going about it versus dynamic?
Yeah, so I actually did a talk on dynamic programming because I looked up a bunch of other algorithms too. And generally speaking, like some of the other ones are pretty intuitive. So dynamic programming you're not going to figure this out on the spot, this like method, but there's a lot of problems that you're going to see on a technical interview that you can't really solve any other way efficiently. Like you're going to get a lot of these questions and you either know it or you don't. And so these are going to be dynamic programming problems.
Cool.
Yeah, I have to say that I've watched other videos on dynamic programming, and while I learned the method that you could use, because like you can just follow the method and populate the table, I've never really understood why you have to do that. It's just like kind of like magic, and it's like, here's how you get the answer. You did a really awesome job of explaining not only how, but also the why behind it. So that was really fascinating.
Thanks. I actually have like I have 2 more slides that go over the change problem. Can I just like quickly show that too? So you guys have the answers in case you guys want to quickly do it yourself. Okay, so
Yeah, when you get these uploaded, just make sure you give me the whole slideshow. I'll put everything
okay,
up for you too.
cool. So the change problem, like it's the same idea. So if we have coins worth 1 cent, 2 cents, and 3 cents, how many ways are there to make 5 cents? So this would be the solution to the to the case with how many ways are there to make 5 cents. And so basically you go through the same reasoning, which is, okay, all the different ways to make coins with 1, 2, and 3, we can pretty much split it into 2 cases, ways of making coins that involve the number 3 and ways of making coins that don't involve the number 3. And so the algorithm then becomes the number of ways to make 5 with 1, 2, 3 is equal to the number of ways to make 2 with 1, 2, 3 plus the number of ways to make 5 with 1 and 2. So I'm not expecting to get it right now because this would be like, you know, if they give you this problem, they're probably going to give you like 30 minutes to an hour to solve it. But this would be the general algorithm, and this would be the Ruby code for it.